Let me show you an example and then I will come back to this statement. So, let us look at this example here where I am generating two signals, both of them are uncorrelated. They are individually coming out of autoregressive processes, which means individually y and u are correlated. Internally there is a correlation between them. This is called internal correlation, what we call as sorry, autocorrelation. It is also known as internal correlation. So, there is an internal correlation in y and u, but there is no cross correlation. Why? Because the generating white noises are uncorrelated. E1 and E2 or EY and EU are uncorrelated. The sources themselves are uncorrelated, or E1 and E2, whichever way you want to look at it. Now, let us generate 512 observations, just a number, and this is a broken cross reference, I am going to remove that. So, here what you see on the bottom is the cross correlation. We know that the truth is that they are uncorrelated. Then why do we have a cross correlation here? What do you think? What is the explanation for observing this kind of a correlation? We have generated uncorrelated series, agreed? Therefore, I should have expected to see a negligible correlation, cross correlation. What you see on the bottom is a cross correlation function. But we do see a significant correlation. Why is that? That is because of the internal correlation. You can see, suppose I am just taking a different example. Suppose that I am looking at now yk and uk, right. Let us write a generic expression. I am looking at these two series. So, I am looking at correlation between y and u at some lag, which is expectation of yk. Let us assume 0 mean signals just for simplicity. This is the definition of cross covariance, correct. We are looking at theoretical properties here. Then what you are essentially doing is, if you, when you are looking at the cross covariance, if internally y and u are correlated, then that reflects in this definition. That is primarily is, let us assume the case of correlated. It is easier to understand, and so I am going to take a simple example. Assume that the in this example y and u are uncorrelated, but the one that I am writing on the board, y and u are correlated. There is, it's just a pure delay. So, y is simply a shifted version of u. Ideally, based on this relation, I should see the cross covariance or cross correlation peak at lag 1, right, and be 0 at other lags, but that is not going to happen, right. So, substitute this expression here. Let us say that there is some b uk minus 1. So, I get here well, I am going to get here L minus 1. So, what does it tell you? The cross covariance between y and u depends on the internal correlation in u. If the input, if this u, let us say if this u is white, then what we want to see, we will see. What is it ideally we expect to see? The cross covariance peaking at lag 1, becoming being non-zero at lag 1 and remaining 0 at all other lags. But that is not going to happen for a general u. For what kind of u will we have that cross covariance? When u is white. So, now you understand the restriction that one of the signals being white. The actual restriction comes about in deriving the theoretical results that I have given, but I am just illustrating the need for one of the signals being white through a simple example. So, coming back to this example here, primarily you see this correlation, significant correlation because of the internal correlation. Let me put it the other way around. What we call as significant is based on this band, this significance band here. You can blame it on the significance band. You say the significance band calculations are correct only if one of the signals is white, but none of the signals is white here. Therefore, the band that you see here, the dashed line that you see, I do not know how well you can see. So, hope you are able to see the dashed line now. The dashed line is no longer valid now. It may be true that this correlation should be insignificant, it is only a numerical artifact, but this one here appears significant because I am using a wrong expression. The dashed line is valid only when one of the signals is white. So, you can look at it either way. You can say that correlation appears significant because one of the signals, none of the signals is white, or you can say the significance band itself which I am using to term the correlation as significant is not valid anymore. So, what should we do here? The remedy is to pre-whiten the signal. What we mean by pre-whitening is, suppose I am given, I want to pre-whiten U, then I fit a time series model. So, what I do is I fit some time series model. Here there is no issue of ARMA, AR and so on. You just fit some time series model, and now what you do is, instead of working with U, you work with EU. So, you assume, you imagine that U is being generated by EU and then compute the correlation between Y and EU. What is the justification? How can I replace the cross correlation between Y and U with Y and EU? The justification is, if Y and U are linearly related, then Y and EU will also be linearly related. On the other hand, if Y and U are not linearly related, then Y and EU are also going to be not linearly related, but at least then I would have satisfied the conditions required for the significance band expressions. So, when I do that, I am now fine. So, in this case I have pre-whitened both Y and EU. In other words, I have done a similar thing for Y as well. And instead of computing cross correlation between Y and U, now I compute cross correlation between the sources that are generating Y and U. That is the point. Essentially, try to compute the correlation between the sources rather than the series themselves. Why sources, we mean white noise sources. So, this is a very important point to keep in mind. Many miss out this point when examining cross correlation. You will just simply come to the conclusion that, yeah, no, these are the significance band, the cross correlation is significant. But one has to keep in mind this very important requirement that one of the signals is white. What you can do is, you can rework this example in R, right, and see if you get a similar result even if you only pre-whiten one of them, right. How do you pre-whiten, by the way? As I said, you fit a time series model, make sure that the residuals are white and the residuals happen to be here, your EU, an estimate of EU. How do you come to EU? We cannot recover the true EU, that is not possible, but whatever white residuals I achieve are suitable representatives of EU or EY, as the case may be. So, this notion of pre-whitening is quite prevalent in data analysis. So, therefore, it is better to get used to this concept of pre-whitening. Any questions?
Some of the coefficients may not be, like if you fit an AR model, some of the observations may be lost. So, the cross correlation requires that both the observations should be same number of observations.
That is okay. I mean, you basically fit an equal high order model, maybe 10th order AR model, just to make sure that both of them give white residuals and are of the same length. That is a practical aspect, but that is a very minor issue. All I have.
If you are whitening only one,
then you skip the, then you, yeah, that is very important point. You just throw away the initial few observations in Y as well, if you are pre-whitening U. But yeah, good point indeed. Any other question? So, this is a story of CCF. Just have to be careful. Always we are interested in the zero, the truth being zero case, for whatever reasons. So, we will just close this discussion very quickly with the estimation of ACF, where we will again come across the same whiteness test. Now, this ACF of course derives itself, estimated derives from the cross correlation function, and this is once again a biased estimator. Yes, Badra. No, you won't. Sorry? Correct. Like the example there.
It doesn't have a correlation, right? It's an internal correlation.
No, here in this example y and u do have.
So how do we differentiate when we use a CCD, when we pre-whiten on sequence, how do we actually know whether there is a correlation between them or not?
Yeah, so when you pre-whiten, after pre-whitening you still see the cross correlation being significant outside the band at any lag, then you conclude that y and u are correlated.
So in this case it lag 1 it is.
Is there some correlation? I do not see anything.
It should be correlated.
No, this is the example for this process, right?
Which is uncorrelated.
Correct.
So in this case,
I did not simulate this case for you.
we would get a peak
Yes,
of 1.
peak at 1, yeah. Okay. So this is a biased, the ACVF estimator is a biased estimator, and once again we know that it is consistent and so on, but why do we prefer this biased estimator? That is because you can show, if you use the unbiased estimator, the unbiased estimator would have a 1 over n minus model or model minus 1. Read chapter 16 of my textbook carefully, it gives you all the details on this, full details. When you work with the biased estimator of ACF, then you would actually end up with a not a non-negative definite sequence. I am not proving that here, but proofs are available, but that is the main reason why we do not work with the unbiased estimator, because we want to guarantee non-negative definiteness. Where do we where do things get a beating? When I use the ACF to compute power spectral density. At that point I have to guarantee that the power spectral density estimates turn out to be non-negative. That is what essentially non-negative definiteness means. When you work with the unbiased estimator, you are not guaranteed that the power spectral density estimates are going to be non-negative value, whereas this one ensures. Okay. So that is the reason why we prefer to work with this biased estimator. As usual, we have results, and the results that are of interest to us are of the case where the process is white, because that is the test that we repeatedly conduct in time series modeling, before modeling and during modeling. During modeling we are conducting the test on residuals, before modeling we are conducting the test on the series, given series. So in both cases I am testing for whiteness of the series. Now this result says if the process, if the data generating process is white, then the autocorrelation function has an asymptotically Gaussian distribution with mean 0 and variance 1 over n. This is the result that is responsible for the bands that you see in ACF. Long ago someone had asked, how do you come up with the bands, significance bands for the ACF? This is a result that gives you the bands that you normally see in your ACF plots, okay? Which means that you can now use those bands to figure out if the series is white. So that constitutes one test of whiteness. There are apparently, if you look up the literature, there are several tests for whiteness, several. I mean, you can go and usually these results would have come out from econometrics or some statistics. The one test for whiteness uses the significance band result. There is another test of whiteness which is called the Portmanteau test or the Box-Leung-Pierce test, which is based on the assumption that if the data generating process is Gaussian white or is uncorrelated, it does not have to be Gaussian white, then you can show that the autocorrelation estimates possess a Gaussian distribution, that is fine. But furthermore, the autocorrelation estimates at different lags are also uncorrelated. So remember we talked about the correlation between estimates at different lags. This result makes use of that fact, whereas the other one, the other test of whiteness, which is only based on the significance band, does not look at the ACF estimates collectively, whereas this is a stronger version. It can be possible, it may be it is possible that your autocorrelation estimates are correlated at different lags. We are talking about correlation between rho hat of L, not the correlation within the series. So the Box-Leung-Pierce test relies on this fact that when the generating process is white, then the sample ACF coefficients possess a Gaussian distribution and also are uncorrelated Therefore, they construct a statistic based on squared autocorrelation, and we know when I take a bunch of squared uncorrelated Gaussian random variables and sum them up, then the resulting one would have a chi-square distribution. So, the Box-Leung-Pierce test essentially does not look at a single lag, it is looking at a collection of rows over different lags, unlike the significance test which is giving you result at specific lags. In that sense, the Box-Leung-Pierce test is considered to be superior, but then there are results there are in the literature which point out to the shortcomings of this test as well, but then there is no end to it. If you are in an econometrics program or quantitative finance program, then we would go further and discuss many more tests and so on. So, you can look up, there are many other tests, for example, Godfrey test and so on. So, I am not going to go over that, I just want to show you a result here. So, here you have 512 observations of a series, white noise series, and the sample ACF is shown here. Okay. Suppose I am given this series, I want to conduct a whiteness test, then I can use a significance band method to determine whether the series is white. As you can see here, I do not know how well you can see, I will zoom in for you. So, this is so what is happening here? I am sorry, I have not generated this out of a I mean I am not basically telling you whether it is white, let us just do the test. Significance band tells clearly that at lag 1 there is a significant correlation. Now, at lag 2 also there is a significant correlation, and then there are some that go outside, and this is the one that bothers the one that look at this ACF very closely. Say, sir, I saw one ACF estimate going out for a picnic, small picnic outside the significance band at lag 20. What do you think about it? Sounds more like a journalist interviewing someone. So, I would say take these significance bands sometimes with a bucket of salt, because there are some assumptions involved, particularly it assumes that the correlation in the estimates are not there and so on. Whereas the Box-Leung-Pierce test is much better because it looks at the estimates collectively. So, what do the Box-Leung-Pierce, what does the BLP test say? By the way, the box dot test in R does that for you. It gives a Q statistic of this value, which is much higher than the critical value of 31.41. So, the Box-Leung test clearly tells you that the statistic is chi-square distributed and with how many degrees of freedom, right. And the observed statistic is higher than the critical value, therefore, you reject the null hypothesis that the series is white. The null hypothesis here is that the series is white. Of course, you can look at the ACF plot and maybe come to the conclusion that this is MA2, but you should not make any such conclusions that it is definitely MA2. It may give you a hint. This significance band that you have drawn is for what, under what assumption? That the underlying process is white. It is only going to serve the purpose of testing for the whiteness, but not for MA2. You have to rederive the significance bands at lags beyond 2 if you hypothesize that the data generating process is MA2. What I mean is the significance bands are not valid for conducting the hypothesis test of the type whether the series is MA1, MA2 and so on. If it is MA1, theoretically what should be the case? The autocorrelations at lags beyond 2 or from 2 onwards should be 0. So, we should be drawing the significance bands from 2 onwards, but you cannot use these expressions anymore, you have to rederive. Those expressions are given, you can refer to Box-Jenkins, there is a worked out example in Box-Jenkins, but I do not want to go into that, because that is not the foolproof way of determining whether the underlying process is MA1 or MA2 and so on. We only want to know if the series is white or not. Once I determine the series is not white, I will go ahead and fit a model, and I will fit the best model, and I will look at the errors in the estimates of the coefficients, look at the trade off and so on, and then determine the order. This only gives me a starting guess therefore. That is the unfortunate part with the working with estimates. Theoretically we know what signature the ACF has, but we cannot fully use that theoretical result because you have to rederive the significance bands, but that is a pain, you do not want to do that. Rather use this significance band or the BLP test for determining whether the series is white, and if the series fails the test of whiteness, then go ahead and fit a model of suitable order, right. So, that is the So, that is the thing to remember. These are the commands. I will talk about the PACF coefficients when I talk about the correlation test, when I talk about tomorrow what methods are available for fitting time series models, because the estimates of PACF are derived from estimates of AR models. So, we need to know the distribution of the AR coefficient estimates. The PACF coefficient, remember, at any lag L is the last coefficient of an ARL model. So, the distribution of PACF estimate at any lag L will be the distribution of the AR coefficient at that is of that order. Therefore, we need to look at the time series modeling, which I will definitely talk about tomorrow. There is I will just spend a couple of minutes in talking about the spectral density estimation, and then we will continue tomorrow. So, now that we have looked at time domain properties, we need to look at the spectrum estimation. Remember, spectral density and spectrum are two different things, right, and one has to be really sure whether the underlying signal is deterministic or stochastic, and further whether it is a periodic signal or an aperiodic signal and so on. Now, having said all of that, in practice what are we going to use DFT? Whether the underlying process is deterministic or stochastic, in practice I am going to compute the DFT of the given data record. From the DFT of the data record, what am I going to construct? An empirical power spectral density known as a periodogram. This is fixed. Now, whether this periodogram is giving me an estimate of the underlying spectral density or not depends on the generating process. If the generating process is deterministic and periodic, and if the data has completed integer, if your record has integer number of cycles, then there is no issue. If the data has not completed integer number of cycles, I am just going to skip those recaps. This is your periodogram. We know that finite length effects give rise to spectral leakage. I will come back to the slides perhaps tomorrow. I just want to remind you of the spectral leakage. This is a sinusoidal signal of frequency 0.04 cycles per sample, but I have 109 observations. We have seen this example before. Ideally, I should be seeing a peak in the periodogram exactly at 0.04, but I do not see that because I have 109 observations, right. And in 109 observations, this frequency component does not complete integer number of cycles. That fractional part is giving rise to this kind of a phenomenon known as spectral leakage. Moreover, I do not even have a peak at 0.04 because the binning is different now. The binning is now 1 over 109, that the frequency spacing is 1 over 109, and no bin with this frequency spacing will exactly hit 0.04. So, what is the source of this spectral leakage? You can look at it in different ways. You can say that one, the signal has not completed integer number of cycles, therefore, that fractional thing is causing me a problem, or you can say that the binning is a problem, or you can say that look, the underlying signal is periodic, but I have just looked at that periodic signal through a window, and that window is not so merciful, it can chop off the signal at any point in time. So, the solution to the spectral leakage is typically to re-window the signal. That means you take the signal that you have, the record that you have, apply a different window so that at the borders where the fractional cycles are being seen, that is being kind of mitigated, and that is where the use of window functions are used. So, there are a number of window functions that people use. rectangular is the default one. That is, you have this signal here which you are observing. This is an infinitely long signal, but perhaps you are only looking at this window. So, you have just abruptly cut off, right. Of course, I have not drawn properly, but you have just abruptly cut off. This is essentially the window through which you are seeing this infinitely long procession of the periodic signal. The windowing methods essentially now apply a different window here to the same data record. So, for example, I could now multiply this signal with a window, so that you can see the window is gentle at the borders, so that the signal is not abruptly cut off at the borders. By default, by observing the signal over a finite time, you are applying a rectangular window, and this rectangular window is distorting the true spectrum. The introduction of these windows, so there are different windows you can see. There is the dashed line here is the corresponding to the rectangular window. All the other windows improve the spectral leakage behavior. But there is only one point that I want to make, and we will continue tomorrow. As you use these window functions, you may mitigate spectral leakage. That means you may suppress the power in the neighboring frequency bins, but the effective frequency resolution. What is the frequency resolution here? 1 by n. That is only when you use a rectangular window. When you start using these other windows which are like bell shaped functions, there are a number of windows, Hamming, Hanning, Blackman, Kaiser, and so on. Okay. So, all these windows are being gentle at the borders, but effectively if you look at it, it is reducing the number of observations. You can look at it that way. You no longer have, it is like the degrees of freedom are coming down. You no longer truly have n observations, but less than n. As a result, the frequency resolution also drops. There is, this is, you can think of as a trade off between bias and variance, although we do not talk of bias and variance in the deterministic world, but that is essentially yours. What you lose is your ability to resolve between two closely spaced frequencies. The moment you start windowing, but you cannot help, you want to reduce the spectral leakage, you apply a window function. What you have to keep in mind is, whenever you apply a window function and construct the periodogram, by the way, when you apply a window function and construct the periodogram, it is called modified periodogram. So, when you work with this modified periodogram, then, and for example, you look at the spectrum command in R, there is something called taper. How much fraction of the data you want to taper off, it is asking. You can specify that. It can also allow you to specify the kind of window that you want to apply. There is a package called SAPA for spectral analysis, but that is more meant for stochastic signals, which I will talk about tomorrow. So, tomorrow for the first 10 minutes or 15 minutes, we will talk of spectral density estimation of stochastic signals. This is for deterministic signals, and then we will discuss finally the topic of estimating time series model and a bit of forecasting. Okay.